All right, welcome back. This is video 11D. Moving right along with probability rules. We've got two to cover in this video. The first one is the addition rule for disjoint events. So first of all, what are disjoint events? Events are disjoint if they cannot occur at the same time. In other textbooks or other places, you may see the words mutually exclusive. That means the same thing. If two events are mutually exclusive, they cannot occur at the same time. And if we have two disjoint events, event A and event B, they both can occur at the same time, then the addition rule says that the probability that A or B, the probability of them occurring, is just the probability of A plus the probability of B. And so if we look, we'll go back to the attendance example as an example of disjoint events, and we'll see this rule. We've actually already used it before, just didn't call it by its name. So back in with the attendance example, this is 24 students in a statistics class. What's the likelihood that 24 students are present, 23, and so on? We had this probability distribution. All the outcomes here are disjoint. We can't possibly have a day where there's 24 students present and at the same time the maximum in attendance is 23. It's got to be one or the other. Those events are disjoint. Every single one of these is disjoint. None of them can occur at the same time. So if we wanted to know the probability that 17 or fewer students attend, 17 or fewer would be these. Since these three events are disjoint, we can use that addition rule and simply add them up. And we've done that already with a problem like this, but weren't formally using this rule. And so the likelihood of 17 or fewer students being in attendance is 0.10 or 10%. And again, we just simply summed up those three events because those events were disjoint or mutually exclusive. They can't happen at the same time. All right, next example. Moving away from attendance. This is something called a Venn diagram. So we have a Venn diagram. The Venn diagram shows the probabilities that a Cecil College student has been to Canada or Mexico. We want to know if the events are disjoint. Something that might be a little bit hard to see, we often enclose this in a rectangle here. So these are the students that have been to Mexico, these are the students that have been to Canada. Outside the box, these are the students that have been to neither country. And we want to know if they're disjoint. Is it possible that a student has been to Mexico and to Canada? Could there be someone in the room that that's happened to? And the answer is, of course, that it could be. That's why these circles are drawn overlapping. These are the students right here that have been to both countries. And so since there are students that have been to both countries, these events are not disjoint. So are the events disjoint? No. Some students have been to both countries. All right, what if we wanted to know what's the probability that a student's been to both countries? We see the likelihood that they've been to neither. We know the likelihood that a student's been to Mexico. The students over here, in this part of the circle, they've been to Mexico, but they've never been to Canada. Over here in this part of the circle, we see the students who have been to Canada, but have never been to Mexico. I think we're going to try to figure out the likelihood that a student's been to both countries. Make sure, there's part B. So what's the probability that you've been to both? Well, that's the students right in here. All right, how can we figure that out? We're not going to use that addition rule for disjoint events. Our events are not disjoint, so we have to use one of the rules from the previous video. So one of the rules from the previous video said, hey, the sum of all the probabilities of all the simple events, they better sum up to 1. And so if we look at the probability that you've been to neither country, the likelihood you've been to Mexico, the likelihood you've been to Canada, and the likelihood of a student having been to both countries, those 4 probabilities, they need to sum up to 1. So we can use that fact to figure out what this is. So I'm going to take 1 and get rid of the probabilities that I know what they are. All right, and if we sum up the probabilities that we know, these probabilities sum up to 0.95. So that must mean that there is a 0.05 or a 5% chance that a student's been to both countries. And so we could even, on your Venn diagram now, we could even fill in that this is 0.05. And when you have a diagram like this, then if the whole thing's filled in, all your probabilities will sum up to 1. All right, next question, part C. What's the probability that a student has been to Canada? All right, here are all the students that have been to Canada. We want to take everybody in this entire circle. And so we're simply going to add up the likelihood that a student has only been to Canada and the likelihood that a student has been to Canada and Mexico. And we'll have the likelihood that a student has been to Canada. So if we add 0.05 and 0.27, we get 0.32, or as a percentage, 32% of the students have been to Canada. All right, we're going to move on and look at a second rule in this video. And so the second rule we're going to look at is what's called the multiplication rule. And this is for events that are independent. So what's it mean for events to be independent? 2 events are independent if the occurrence of one event does not influence the probability of the next event happening. And we've sort of talked about this with the attendance problem. The likelihood of perfect attendance on one day, does that affect the likelihood of attendance on the next class? Probably not, so those would be independent. So if we have independent events, we have this multiplication rule. The multiplication rule says as long as you have 2 events that are independent, so A and B are independent events, the probability of them both occurring, of A and B occurring, is the probability of A, multiplication rule, times the probability of B. And this only works if A and B are independent events. So we want to see how this works. So let's look at an example with this one. Turns out, too, we'll actually be able to extend this rule. What happens if you have 5 independent events? So we'll get to that in a minute. But okay, let's say we flip a fair coin multiple times. Each flip is independent of the previous flip. So, you flip a coin, it lands heads or tails. No matter what the outcome is, the next time you go to pick up that coin, the probability of getting heads is 50% or 1/2, and the probability of getting tails is 50%. So flips of a coin are independent. So since they're independent, what's the probability that if I flip a coin 2 times in a row, what's the probability of flipping and getting heads 2 times in a row? So I'd like to know the probability that I get heads on the first toss and I get heads on the second toss. Now, since the first toss of the coin and the second toss of the coin are independent, because they're independent, I can use that multiplication rule. And this is the probability that we get heads on the first try times the probability to get heads on the second try. Doesn't matter what try it is, the likelihood of getting heads when you flip a coin is a half. So this is just going to be 0.5 times 0.5. Or a 25% chance of flipping a coin twice and getting 2 heads. All right, we can extend this. In part B, I think we're going to extend this. We're going to flip a coin instead of twice. We're going to do this 5 times. So now we flip a coin 5 times. What's the probability of flipping and getting a tail 5 times in a row? Each of those 5 flips are all independent. The first flip is independent of the second, independent of the third, the fourth, the fifth. So we have 5 independent flips. And we want to know the probability that we get tails, and tails again, and tails again, tails again, and tails again. That multiplication rule extends. It doesn't matter if you have 2 independent events or you have 25 independent events. As long as they're all independent, it says the likelihood of all of those events happening, you simply just multiply those all together. So this will be the probability of getting tails times the probability of getting tails. And we'll have this here 5 times. And we know that for each one of these, the probability of getting tails is 0.5. Now, I'm starting to kind of get tired about writing all these tails here 5 times. I could write out these probabilities 5 times. Hopefully you know that instead of writing 0.5 up here multiplied out 5 times, that there's a shorter way to write that. Five times isn't so bad, but if we did this 25 times, you certainly don't want to write that out 25 times. The shorter way to write that is this is 0.5 to the 5th. Be careful, don't take 5 times 0.5. If you take 5 times 0.5, you'd get 2.5. 2.5, is that a valid probability? Is that a number between 0 and 1? No, it's not. So that's certainly not the right answer. So be careful. 0.5 multiplied by itself 5 times here is 0.5 to the 5th. And if you computed that, we would get just over a 3% chance of flipping a coin 5 times and getting 5 tails. All right, one last one with independence. At Cecil College, roughly 2/3 of the students are female. And let's say we randomly select 4 students to represent the college at a retreat. Now we're randomly selecting them. So since we're randomly selecting them, they should be in their gender, should be independent of one another. What's the probability that the group is entirely female? So we want to know the likelihood that the first student's a female, and the second student, how many do we have? 4. And the third and the fourth are all female. Since they're independent, and that comes from here, how we selected them, we can use that multiplication rule for independent events. So I'm just going to take the likelihood that the first student's female times the likelihood the second one is, the third one, and the fourth one. And the likelihood of each student being female, it says 2/3 of them are female. Again, we could have 2/3 times 2/3 times 2/3 times 2/3. Or the quicker way to write that would be 2/3 to the 4th power, 4 of those. If we raise each of these to the 4th power, we'll get 16 over 81 as a probability. That's 0.1975, about a 19.75% chance of selecting 4 students at random from the college and having all 4 of them be female. So one more application of the multiplication rule for independent events. That's it.